Okay, so continuing with 1105, I'm going to talk about the period and the amplitude of trig functions. So if we've got y equals k sine ax, k is the amplitude of the function. You multiply a function by something, it's going to increase it or decrease it. And then the period is 2 pi over a. Because it's the same. The amplitude is k, the period is 2 pi over a. Now if k was negative, as with any function that we make it negative, that gets flipped through the x-axis. For tan of course has no amplitude, there's no top and bottom, it goes to infinity in either direction. The period of tan is smaller, so the period for tan is just pi on a. So normally if you've just got sine x, then a equals 1, and the period is 2 pi that we talked about. So if a was 2, the period would be pi. So sine would just fit into just from 0 to pi. So here's a sine curve, and instead of being, so if a equals 2, instead of this being 2 pi, this would just be pi for that one. So it's, what would happen is up to 2 pi, you would actually fit 2 periods. Okay, so I quite like to think of it that way, that if a equals 2, then you fit 2 of them up to 2 pi. But you can also think of it as 2 pi and 2, so one of them fits up to pi. And that works the same for cos and the same for tan. So I'm just going to look at the results of the investigation. Now I'm just graphing sine here, but the answers for sine and cosine are exactly the same. I will do tan separately in a minute. So I've got the k and the a here with sliders for each. First I'm going to play with the slider for k. So as I make k bigger, you can see things stretch vertically. That is called a vertical dilation. And if I make k smaller, it gets smaller. If k goes negative, it reflects through the x-axis. Now k changes the amplitude of the curve. So if I set k to be 2, the amplitude is 2. The distance from the centre to here equals 2. So k is the amplitude. When k is negative, we still say here the amplitude would be 3.3 because the distance from here to here is 3.3, or from there to there. So the amplitude is 3.3, but it is reflected through the x-axis. Now I'm going to put k back to 1, and we're going to look at a. Now what we can see is as I make a bigger, the curve dilates towards the y-axis. The period reduces. A bigger a means a smaller period. If I set a at 1, the period is 2 pi. We get one cycle of the function going to 2 pi. When I set a to 2, the period is now pi. We can actually fit 2 of them up to 2 pi. If I change it to 3, we can now fit 3 periods up to 2 pi. So the period, just one of them, is 2 pi divided by 3. If we divide 2 pi up into 3 pieces, we have 3 periods. So the period is 2 pi over this number. If I make a negative, just like with other functions, we get a reflection through the y-axis. Now, in this particular case, because sine is an odd function, it actually looks the same as if there was a reflection through the x-axis, but it is, in this case, a reflection through the y-axis. So a negative and a positive, if it's 2, negative 2 or positive 2, we're still going to fit 2 periods into 2 pi. So the period would just be pi. Now let's change this to tan and have a look at the results for tan. So if I make a equal to 1 and k equal to 1, then that's just y equals tan x. Now changing my k here still does a vertical dilation. It stretches it vertically. It stretches it up and down. If my k becomes negative, I do reflect through the the x-axis. okay? So it stretches it up and down. It stretches it away from the x-axis. Now, in terms of showing that in a graph, you should always graph the intercepts and one other point. So when k equals 1, this point right here, which is pi on 4 and 1, is a good one to graph. If k was a bit bigger, say 2, then pi on 4, you would get 2. And just marking that point on your graph demonstrates that, but the shape is still the same. You can even draw the shape and then put in a point later. Just say in your calculator what happens if x equals pi on 4, sorry. You get 2 and you mark that point on your graph. I'll put k back to 1. Now let's change the a. So at the moment the period for tan is pi. We've got a half pi that distance and a half pi that distance. So this whole piece of tan fits in a distance of pi. Now, just like with sine, if I make a bigger, it squishes it towards the y-axis. So if a equals 2, instead of going from negative pi on 2 to pi on 2, it now goes from negative pi on 4 to pi on 4. So in that same distance we had before, we can fit 2 of these periods. So the period for tan is pi over a. For sine it was 2 pi over a because the original period was 2 pi, but for tan the original period is pi, so it's just pi on a. So again, if I make a equal to half, then we can see it's much wider. It's actually, the period's now 2 pi because pi divided by half is 2 pi. So negative pi and pi, the distance between those two is 2 pi. If I make a negative, of course I'm going to reflect through the y-axis. Okay, make the x negative, it reflects through the y-axis. Make the k negative, it reflects through the x-axis. Because tan is an odd function, it really looks the same either way. So I might just clear these graphs and show you what I mean by that. If I graph y equals tan x, and then I'm going to, actually let's make that negative x. So negative x is reflected through the y-axis, but y equals negative tan x is reflected through the x-axis, but it's the same graph. Because it's an odd function, we get the same result. So let's have a go at graphing a couple of these. So the first one is 3 sine 2x. So it's not a bad idea to write down what the period and the amplitude are. So the amplitude here is 3. And the period is 2 pi on 2, which equals pi. So this is the same as what I mentioned earlier. So up until pi, you're going to fit a whole cycle. So you'll get half the cycle to here and the whole cycle to there. Now in between, the peaks are going to go up to 3. Now you can set 3 anywhere here. You can just say, okay, let's make that 3 there. So it's going to start at 0, go up to there, down here to negative 3, and finish at pi for one period or one cycle of a sine wave. Now we were asked to graph it from 0 to 2 pi, so we do need to repeat that again with another one. So there's your solution to that one. We've got one for cos as well. Now this one is negative, so it's going to be flipped through the x-axis. So instead of starting up here, it's going to start down here. The period there, of course, is 2 pi divided by half, okay, which equals 4 pi. So we're only actually going to fit half of it into this from 0 to 2 pi here. The amplitude is 2. Even though we've got negative 2 there, the amplitude is 2 because that's the distance from the center to the peaks. So instead of starting up here, we're going to start down here because of the negative, and we'll call that negative 2 because the amplitude is 2. Now normally we would go down to 0 and back up here if a equal 1. Okay, but we've got to spread that out a little bit further. Instead of going there to there, we've got to get to here. So what you can do with these if you want to, another method, oops, I've gone a bit high there. Another method would be to actually draw them first and put the numbers on later. So if you wanted to, you could draw like a normal cos curve that goes like this. That would be 0 to 2 pi normally. Okay, so that would normally be 2 pi, but because our period is now 4 pi, 2 pi comes back here to the middle. So that would be 2 pi here. This would actually be 4 pi for one full period. And you've only been asked to graph that bit there. So you can always draw it first and then sort of rub out the bits you don't need. So I could draw that and then go back and rub all this out if I wanted to. And of course I need my -2 and my 2, so I also need a 2 up here. Okay, this is tan 3x, 2 tan 3x. So the period here will be pi on 3. Okay, that's pi over a. Now, in terms of drawing this one, the first thing I'm actually going to do is just put in some asymptotes, because I know I'm going to need asymptotes. So there's an asymptote. Now I go twice that distance away from my next asymptote, twice that distance away for another asymptote, and then I'm going to start working on drawing my curve, and I'm actually going to put the numbers on later. So I'm just going to draw a normal positive tan curve. So normally it goes through a point around there, and it goes up, goes there, 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 and I'm actually going to do this first and put the numbers on later once I've worked those out, because I know the shape of the curve is going to stay the same. Now normally from this distance to this distance, or from there to there, is pi, but now we're actually going to fit 3 of them into that distance. So because it's pi on 3 for one period, what I want to do, this distance from here to here will actually be half of that, because it's half on this side and half on the other side. So this number here is going to be pi on 6. So over there would be negative pi on 6. It's a pi on 3 distance. Now, so the next one will be pi on 3 away. Now what you can do to work that out exactly if you want to is bring in your calculator and go 1 over 6 plus 1 over 3. And that's half. So right there is pi on 2. And now I'm going to add another 1 on 3, or it's actually pi on 3, but I'm just looking at what the fractions are. So 5 on 6. So this one is 5 pi on 6. And at this point you may realize that we do actually need more. Let's just write some numbers on the x-axis. We need to get up to 2 pi. I hope I've left enough room over my page. So another 4 squares along. I'm just going to press equals again on my calculator. That one's going to be 7 pi on 6, and then press it again. I've got 3 pi on 2, or 1.5 pi. And as you can see, I am running out of space. The next one would be 11 pi on 6. And 2 pi is going to be a little bit beyond that. The next one would have been at 13 pi on 6. So I haven't even actually left enough room on my page. So you do have to be a little bit careful with that type of thing. So I just changed the question slightly from 0 to 11 pi on 6. Obviously you can't do that in an exam. So if something like this happens in an exam, just make it again a little bit smaller. You could put the asymptotes closer together. But let's just keep this looking nice. So I'm just drawing those on. And now the last thing I need to do is work out vertically what my numbers are. So what I'm going to do for that is get out my calculator again and work out what this is. Now it's half of this, so it's going to be pi on 12. Okay, if I've got 1 on 6 and I divide it by 2, I get 1 on 12. So that's pi on 12. So in my calculator, I'm going to put that into there. So 2, let me just make sure I'm in radians, which I'm not. So radians. So I'm going to go 2 tan 3 times pi divided by 12. You can use the fraction button if you want to, and that gives me 2. So I know that that value there is 2, and that gives me a really nice scale on my graph. We could put the -2 on as well. So that's the process I would use for that. You can use that same process for sine and cos as well, where you graph it first and put the numbers on later. But obviously, you've got to look out for that situation where you might just run out of space. We would need just one more square on the page to fit all the way to 2 pi, unfortunately. I should have just started further to the left. But it's good for you to see that happen. Okay, so a phase shift is a left and a right shift. So this value b moves the entire function left and right. Now if b is a negative number, it moves to the right. And if b is a positive number, it moves to the left. So b greater than 0 positive moves left, b less than 0 moves right. Okay, so let's have a look at this example with phase shift. We're asked to graph y equals 2 sine x plus pi on 3 on negative pi to pi. The period is one cycle, so 2 pi on 1, so 2 pi. This distance is 2 pi, so this is literally going to be one cycle of a sine curve, which is important to recognize. The amplitude is 2. The phase shift is pi on 3 left. Okay, and you do need to right or left on that. Now, a little trick for these is to use a scale over 3. So if I make this 0, I might want to make this one pi on 3, this one 2 pi on 3, and this one to be 3 pi on 3, which is just pi, which is the end, and the same thing in this direction, negative pi on 3, negative 2 pi on 3, and negative pi. By using this scale, it's really, really helpful for us. Now let's throw in a y-axis there. Now, of course, because the amplitude, is 2, then the top of our curve will be 2 and -2. You can put those numbers on at the end if you want to. Now, originally, our curve would have gone right through here, but it's been shifted. This piece here has been shifted pi on 3 left. So that bit's now going to go through there. Normally, it would go up and come down at pi. So normally it would go up and down there. But this bit that normally goes through here has been shifted pi on 3 to the left, so that's going to come down there. So the top is going to be halfway between, which is there. So I'm going to draw that on. Okay. Now, I'm going to think past this point. So this distance here was 3 squares. So the bottom would actually be here, but I don't need to draw it quite that far. So that's there. And the same thing in this direction. This distance to the peak, 3 squares, so 1, 2, 3, there is a peak there that I will need to draw. So let's draw that in. And then I do need to start coming down again. Now, it's a really good idea with any graph to also mention what the y-intercept is. So if I put 0 in here, so for the y-intercept, so where x equals 0, I've got y equals 2 sine pi on 3. Now from our exact value triangles, this is sine pi on 3 is root 3 on 2. So that whole thing is the square root of 3, 2 times root 3 on 2. So that value right there is the square root of 3, and it's good to give that. Ideally, it'd be good to give this value as well, which actually by symmetry would be negative pi on 3. Okay, so that there is pi, negative root 3, sorry, negative root 3. There's a lot of symmetry in these curves, and that same value over there is negative pi and negative root 3. So giving all those important values, all intercepts, all turning points, all end points is really, really important. One thing about this curve is that value there and this value here are going to be the same. this one here, which is this distance from here to here, should be the same as this distance from here to here, which actually shows I haven't drawn it very well because that's not quite as symmetrical. So I'm just going to put it all together. So if we've got k sine ax plus b, notice that's factorized, plus c k cos ax plus b plus c, the results are the same. The period for both of those will be 2 pi over a. The amplitude for both of those will be k. The center, that's an up or down movement, and that's the c. So if c is positive, if c is greater than 0, then it's up. If c is less than 0, it's down. So that's an up or a down shift. The phase shift is your b, right or left, as already mentioned. For tan, the only thing that's different is the period. The period is pi on a instead of 2 pi on a. Amplitude doesn't exist. Center is still c, and the phase shift is still b as before. Okay, so this is about as hard as these ones get. That could be slightly harder for a really challenging one. So firstly here, the period is always going to be 2 pi over this number. So the period is 2 pi over 2, which does equal pi. So one cycle in pi units. Now the amplitude is 3. The center is this number at the end. So this graph has been shifted up 1. Now to work out the phase shift, we must factorize this. So 2x minus pi, we need to put a 2 out the front. Now you need to work out what goes here. That's going to be minus. So this times that equals pi. And what you end up getting is this number comes down underneath. So pi on 2. If you multiply those, you will have that. So the phase shift here is pi on 2 to the right. Okay, so let's actually have a go at drawing this curve. So remember I said whatever the phase shift is gives you a bit of your units here. But the first thing I'm actually going to do here is graph the center and the amplitude. So my center is going to be at 1 unit and my amplitude is going to be 3 units higher than that. So I need to go up to 4 up my axis, and I am actually going to use the squares on the page for my 1, 2, 3, 4. So 1, 2, 3, 4. And I've got -1, -2. I need to be able to go down 3 from here as well, and that gives me that space down to -2. And what I tend to do is I actually draw on where the center is just with a very light dashed line, or even just dots along there, just to help me. That's where my center is. It just gives me a bit of guidance. Now I'm moving pi on 2 to the right, so I want my units to, I need pi on 2 as a bare minimum for my units. So, but I'm actually going to make pi on 2 here. I'm going to, so this will be pi, this will be 3 pi on 2, remember that's 2 pi on 2, and this is 4 pi on 2, which is the same as 2 pi, so that's where my graph is going to stop there. Now normally, without the phase shift, we would start up here on the y-axis, and because the amplitude is 3, it would be 3 units above the center. So normally we'd start here, and just in light pencil, I'm going to draw what it would normally look like. So it would normally start here and finish over here. Okay, halfway between at pi, it's going to be 3 units below. That's what it would normally look like. Here it's in here, halfway between each of those, it would normally cross the axes. That's what it normally looks like, and I'm going to start with that. Now because my period is now pi instead of 2 pi, if I wanted to I could just rub this out and make it pi and draw another one, but what I'm going to do is I'm going to squish that in. I need to fit 2 of them in that space, so this point I'm going to bring halfway back, okay, which means this point is going to be halfway back, and in this case it would look like this. And again, I'm going to draw this really lightly with pencil in an exam, and I'm going to do a second one. So you can see it's almost like gradient really. It goes across 1, down 3, across 1, down 3, across 1, up 3, across 1, 3, 3, So to here, back to there, and back to there. So that's still just lightly with pencil. But now I also need to take into account that everything is going to be shifted pi on 2 units to the right. So this point right here now ends up right here. But I'm still going to follow that pattern of across 1 down 3. So I'm going to draw it there, and I'm drawing it now properly with pen. So across 1 down 3, across 1 up 3, across 1 up 3, across 1 down 3. That's where it finishes, and that's really handy as well that it's down there at -2. It's always a good idea to check that y-intercept. So if I put 0 into the original function, it's 3 cos of 2 times 0 minus pi. Oh, I got some extra brackets there. Plus 1. So my y-intercept is at -2. We could have even started with that if we wanted to. So that was a nice one for putting it all together. So we can see it's gone up 1. We have 2 of them from 0 to 2 pi. Because of that 2, it has been shifted pi on 2 to the right, and it has an amplitude of 3. So we've taken all of those things into account. The way these questions get harder is when this is a fraction. Sometimes you'll be given it fully factorized already, and sometimes you won't. I am going to do one more really hard example like that. Okay, so this is a pretty hard one. With a really hard one, I doubt you'd get 10. It is possible, of course. This is really testing things here. Now, the first thing to think about is that 3x plus pi over 6. I would separate that into 2 fractions. So 3x on 6 is the same as x on 2 plus pi on 6. Now, we want half to be up the front because we want it factorized so x is on its own. And we need to work out what goes here. Now, because this is half, it's half times something would give us the 6. So that's going to be 3. So our period is 2 pi divided by half, okay, which equals 4 pi. And our amplitude is just 1. Our center is just 0. So let's have a look at our phase shift. Sorry. Phase shift is now pi on 3 left. Okay, so I want units that are thirds. That's the easiest way. Now, pi on 3 to the left, we already saw that one in a previous example. Let's just say on 0 to 2 pi. So I'm just going to take note on here where negative pi on 3 is, even though I don't have to graph it to there. So this is going to be my 0, this is going to be pi on 3. So this is going to be 2 pi on 3, and this is going to be 3 pi on 3, this is going to be 4 pi on 3, 5 pi on 3, and then 6 pi on 3, which is 2 pi. Now, because my period is 4 pi, I'm only actually going to fit half a cycle from 0 to 2 pi. It's sine, so it would normally start at 0, but it's going to start to the left there. Now, again, I am going to just sort of dotted draw what I would do. So let's just put a y-axis on there. Because my amplitude is 1, I'm just going to say that's 1 and that's -1. I can, if I want to, find out what my x-intercept is. That'd be sine of pi on 6, which is actually half. So that's nice and handy to know that value. So y-intercept, sorry, I think I said x-intercept. So y-intercept is sine pi on 6, which equals half. It's always nice to have those intercepts. Once we learn how to solve these equations too, you could solve it to find the x-intercepts as well. Now, what I'm going to do is draw a normal sine curve from 0 to 2 pi with a period of 4 pi. So I'm only going to draw half the cycle from 0 to 2 pi. So normally that would look something like that. Really light dotted. I did intentionally try to aim to go through there because that looks like that there is there. So all of that is going to be shifted pi on 3 to the left. So this point up here is now going to be there. This point here is now going to be there. So let's have a go at drawing that. So I'm going to do a nice curve up like that. I did not need to draw this bit. I might actually just rub that out because I'm only graphing from 0 to 2 pi. Now that point will also be there because of the symmetry of the curve. So you can see here, across 4, up 1, down 1, across 4. So I would get a similar pattern down here. So there's going to be a point here. Now I could check that by putting that into this equation to find out what that coordinate is, and that's really important. So if I put 2 pi in here, that's going to be 6 pi plus pi, so it's going to be 7 pi on 6. Now 7 pi on 6 is the same as pi plus pi on 6. Okay, so I'm down there where that's pi on 6. All stations to central, it's negative. Pi on 6 is half. Okay, sorry, sine of pi on 6 is half, so negative half. And that makes sense there. There's my 0, there's my negative half. So the coordinates of that point is 2 pi negative half. But it makes sense because across 2, up 1, up, well, half in this case. Okay, the distance from, because from here to here, okay, oh, well, it would have actually come down, but the point where it reaches the center here is 6 across 2 up. So that would be the same thing back here. I would end up over here somewhere. I've just got to look at that whole symmetry of the curve. The center is 0, so that point there is on the center. So what I'm really drawing down here is a repeat of this section bit underneath. So this is the 2 across 1 up bit from here, 1 down 2 across, because that is the center. That works. Okay, so I just wanted to look at putting it all together on Desmos. So you can see here I've got k sine a x plus b plus c. I'll start with the plus c because we haven't looked at that one before. So making c go up shifts the whole curve up, and making it go down shifts it down. And we've seen that before with other functions. So if I set c equal to 1, you can see the very center here is 1. Now I'm going to change the amplitude there to 2. So what you can see, the center is still 1, but the distance from 1 to there is 2 units. Okay, I might just change that on my, there we go, we've got all the numbers now. So the center is at 1, but from the center to the peak is 2 units for my amplitude to be 2. So this distance is 2 units. Now let's look at the phase shift. So at the moment I've got the phase shift equal to 0. I might just put my center back down at 0, so it's a fairly typical looking curve. Put my k back to 1. Now I'm going to move my phase shift. So I'm going to make it positive. So the curve is going to shift left. It's shifting left. As I go back to 0, now I'm going to make b negative, and it's going to shift to the right. So there we have it. Those are all of the transformations of the sine curve. Now if I change it to cos, the results are the same. Let's put b back to 0. So if I change my amplitude, sorry, that's not my amplitude, that's my a, that's my period. If I change my period, I make it bigger, it shrinks. I make it smaller, it spreads out. I make it negative, it reflects it through the y-axis. Okay, let's just put a back to 1. If I change my amplitude, it stretches it up and down, negative flips it through the x-axis. Let's go back to 1. My B shifts it right and left. Positive shifts it left. Negative shifts it right. And my C is my center, so that's my up and my down. Whatever that is the center of the curve. It's well worth having to play with these yourself as well.